2. And chapter 2, this one entitled Physical Properties of Pure Compounds. So we have 4 points we need to cover in this chapter. First, we need to start what is meant by pure compounds or pure substances. So this type of component that we will deal with during the whole chapters that we have during this semester. Then we will explain phase diagrams and some of the interrelations or relationships between thermodynamic properties. And we will explain forms and sources of physical property data, how we can obtain or get values for these thermal property data. And then, if we don't have this data exists, if we don't have figures, if we don't have tables contain values for this data, so how can we obtain these data? Then we will start talking about the thermodynamic models for these physical properties. Okay, so then we have some models that we can use in order to calculate this data that we have. And then the objective of this chapter to be able to use or to obtain this physical property data either from graphs or from tables or from the models. And the models that we'll explain, these are the equations of a state. So for sure you have some information about this one. So let's start with the first one. What is pure substance? So basically any substance, you can call it a pure substance if it has one of the following conditions. If this substance has fixed composition, or this substance is a multi-phase system, but still we have some uniformity in the composition, or this substance, or can we have mixture, but this mixture is homogeneous. So we have 3 conditions. Any one of them, any substance you have, any mixture you have that fits in one of these categories, okay, can be described as a pure substance. You can use pure substance equation to describe or to know the behavior of this substance. So what are the examples of each one of them? So let's start with the first one. We have fixed chemical composition substance. This one, if you have any substance, this substance has fixed chemical composition. Which is the most logical. Similar to nitrogen. If I tell you I have nitrogen, for example, this is pure substance. I have only nitrogen. I have helium. This is pure substance. Only one compound exists. Okay, so this is a pure substance. Water, carbon dioxide, either carbon dioxide that has carbon and oxygen, but this is still a pure substance. Okay, so it's not regarding the atoms, different atoms. Even different atoms can form a pure substance. The other category is homogeneous mixture. If you have mixture of different elements, of different compounds, this also can be described as a pure substance if the mixture is homogeneous. And the most common example for this one is air. Air is a mixture of 7 components, for example. Okay, like oxygen, nitrogen, and other components. But if you get air sample from any place in this world, you will get almost the same composition. So this homogeneous or this mixture is homogeneous. So although air, we know that air is mixture of different compounds, but when you are trying to model air or try to calculate physical properties of air, you deem that air is a pure substance. Okay, clear? The last one, the last category is multi-phase systems. If you have system or 2 or 3 phases, also this one can be described as a pure substance if the chemical composition is the same. So what this means, if we have ice and water, for example, so the composition of ice is the same as composition of water. We just have difference in the phase, but the composition is the same. So even if you have mixture of ice, if you have mixture of water exist together, you can consider both of them as a pure substance because they have the same composition. They have different phases, but the composition is the same. Okay, so any one of these cases can be considered as a pure substance. Again, if you have fixed chemical composition substance, if you have mixture, but this mixture is homogeneous, if you have multi-phase systems, but the composition is uniform between the phases that you have within this multi-phase systems. Okay, clear? Okay. In the slides you have, you have some extra slides that describe the difference between atoms, molecules, compounds. So these things from chemistry courses. So you just have them in the slides just in case if you want to refresh your mind with the difference between these terminology. Okay? Okay, but let's continue this one. Here we have talking about phase. So what are the phases that we know that can exist for any substance? How many phases we have? Three main phases. We have more phases, but let's say we have three main phases, which is solid, liquid, and gas. So, and the differences between them is basically the intermolecular forces between the molecules. So in solids, we have the molecules are almost at fixed composition because we have very strong forces between the molecules of the solid phase. While in liquid, the forces are weaker than in solids. So this is why we can see group of molecules in the liquid phase. They can like move, but they move as a group. In the gas phase, the forces, the interaction forces are very weak. So this is why you can see single molecules are free to move within the gas phase. So we have solid, liquid, gas. The intermolecular forces are very strong in the solid, very weak in the gas. So this is why in solid the molecules almost they are fixed, just can vibrate. In liquid you can see group of molecules are free to move. In gas you can see each molecule are totally free to move. And the main differences between them in solid phase, it has definite shape, it has definite volume, and the energy level for it is very low. While the vapor phase, no definite shape, no definite volume, and the energy level is high. Also for the liquid, it has definite volume, but the shape, it doesn't have definite shape, and the energy level for this one is medium. Okay. Any phase can be like, or any substance can change its phase from one phase to another one. And the name for this process are the following. So if you have solid phase, and this solid phase is changing to liquid phase, so this process is called melting. And the opposite for it is freezing. So we have liquid is being changed into solid. Liquid is changed to gas through the vaporization process, and gas through condensation can be liquid. And solid directly can be gas through a sublimation process, while gas can be directly solid through deposition process. Deposition process means gas directly changed to solid with no liquid like in intermediate step. Okay, just gas to solid directly, sublimation solid to gas directly. Okay, so far it's clear? Any questions in these parts? Clear? The second part that we need to focus on today is the phase diagram and properties interrelations. So the idea of this one, in thermodynamics, if you remember, the ultimate goal is to be able to design and analyze different thermodynamic systems, especially any system that deal with energy or have energy transfer. So in order to design or analyze these thermodynamic systems, we should be able to analyze the state of any substance using its properties. And how this happens, you should be able to calculate the value of these properties. But the key here, these properties are interrelated together. If you change one property, the other property also may change. Okay, so these properties are connected together. Okay, so this is why we should consider how these properties are linked together, or how these properties are influenced by each other, because one can change another one. Okay, one of the ways that explain to you the relationship between these properties are the phase diagrams. Okay, and the phase diagrams, these are diagrams just explain how different state variables similar to temperature, pressure, volume. We have some phase diagrams containing or express enthalpy, entropy, but let's focus with the main ones right now just to understand the basic idea. And it describes how these properties are related during phase change. These phase diagrams can be 2D or 3D. So 2D diagram similar to PT diagram, TV diagram. So this P indicates to pressure, and this T indicates to temperature. This V is volume. So an example of the 2D diagram is pressure temperature diagram, or temperature volume diagram. Or we can have 3D diagram, which is pressure, volume, temperature. All of them are plotted in the same figure. Okay. Let's start the phase change process. Let's consider water, for example. We know that if we have water at atmospheric pressure, And at 20 degrees Celsius, let's say this water, we contained it in a piston here, for example, and we start to supply heat to this water. So the initial state water, 1 atmosphere, 20 degrees Celsius. So what will be the phase we have? Liquid or vapor or solid? Liquid. Okay. We are adding heat to this water. What will happen to the temperature? Increase. So let's assume water start to increase, or the temperature of water start to increase by adding heat. And now we have the pressure is 1 atmosphere, the temperature is 100 degrees Celsius. Okay? So what the phase we have right now? No. We're still at liquid. Okay? And if you continue adding heat, so what will happen? Now, phase change will start to occur. Now, vapor will start to appear. So this one here we have vapor, but still we have some liquid. And still the temperature is 100 degrees Celsius. If you continue adding heat to this system, so what will happen? Again, everything now will be vapor. Pressure is 1 atmosphere, temperature is 100 degrees Celsius. So at this temperature, which is 100 degrees Celsius at 1 atmosphere, phase change is happening. 100 degrees Celsius, we have liquid, we have phase change happening, liquid and vapor, and all the liquid will be vapor at the end. So at this 100 degrees Celsius, we have this phase change happening. If you increase the temperature above 100, then we have continue, we still have vapor. And here, let's assume the temperature 300 degrees Celsius, for example. So this is the whole idea. This is the same approach or the same observation you can see for phase change for any pure substance. Mixtures has different behavior. But for pure substance, so we have liquid phase, and then at fixed temperature, at certain pressure, phase change completely will happen, and then you will have temperature will increase in the vapor phase again one more time. Clear? So this is the key here that describe pure substance. For pure substance, phase change is happening at same temperature and also same pressure, not within range. Phase change will not happen between 90 and 100. It will not happen between 99 and 101, for example. Exactly, phase change will happen at 100 degrees Celsius. At 99, 100% liquid. 100.01, it's 100% vapor. Okay? So exactly at this temperature, 100 degrees Celsius at 1 atmosphere, phase change will happen. Clear? Any questions so far? Okay. Now, let's back. So this is the figure we have. And let's focus on these three cases. State number 2, state number 3, state number 4. State number 2, 1 atmosphere, 100 degrees Celsius, completely liquid. State number 3, mixture of liquid and vapor at same temperature pressure. State number 4, we have vapor, complete vapor at same temperature and pressure. So here in case number 1, from number 1, state number 1 to state number 2, we are adding heat, right? And this heat causes an increase in the temperature, right? So we increase the temperature from 20 to 100 degrees Celsius. Here in this case, from state number 4, we are adding some heat, and this heat causes the temperature to increase from 100 to 300 degrees Celsius. Make sense? But from state 2, 3, 4, you're still adding heat. But does this heat affect the value of the temperature? Do you see any change in the temperature between state 2, 3, and 4? So what is happening? Where this heat is going? What difference that you see between state 2, 3, and 4? Do we change the substance?
No.
We have the same substance. Do we change the pressure?
No.
No. Temperature?
Yeah.
No, doesn't change. So there is only one thing to change. State number 2, we have liquid or vapor? Liquid. State number 3, we have mixture. State number 4, we have vapor. So the only thing that changed between state 2, 3, 4 is what? Just the phase change. So here we are adding heat, but this heat will not increase the temperature. So what this heat is doing to the system is just breaking the bonds in the liquid phase. Do you remember the difference between liquid and vapor? So in liquid we have some intermolecular forces, right? These forces in the liquid stronger than what? The vapor. So we need to break this bond so the molecules can be like set apart from each other. So only this heat is going to or doing this action. Just break the bonds between the liquid molecules in order to have each molecule is to be free to move. And then it can be converted or change its phase from liquid to vapor. This is why we have two things of heat, is always described. We have something called sensible heat, and we have something called latent heat. Sensible heat and latent heat, both of them heat you are adding to the system. Okay? But sensible heat, this comes from sense. You can sense it. How I can sense it? You can add heat to the system, and the temperature of the system will change. Okay? If you add heat to this system, the temperature of the system will increase. If you remove heat from the system, the temperature will decrease. You can sense temperature difference. So if you are adding or removing heat from the system, and this results in a temperature change without changing the phase, this is called sensible heat. But if you are adding heat to the system, and you cannot feel any action or any consequences in terms of temperature change for this heat addition, for example, but at the same time you can have phase change. So this type of heat is called what? Latent heat. Okay? Is it clear? So keep this in mind. We have two types of heat. We have something called sensible heat. It only changes the temperature without changing the phase. Similar to what we did from state 1 to state 2. We still have liquid, but the temperature increased from 20 to 100. State 4 to state 5. We still have vapor, no phase change, but temperature increased from 100 to 300. This is sensible heat. But state number 2, 100 degrees Celsius liquid. State number 4, 100 degrees Celsius vapor. We have the same temperature, but we are adding the heat to the system. So this is called latent heat because this heat causes a phase change without changing the temperature. This is very important because I think all of you have mass and energy balance course, right? You have lecture after this. When you start the energy balance term, then you will start calculating each one of them. If you cannot differentiate between these two types of heat and how you calculate them, then your energy balance cannot be done accurately. Okay? So far it's clear? Any questions? Questions? Yep. You. Cool. Okay. Okay. Now let's start the first phase diagram we have, and let's call it TV diagram, which is temperature volume diagram. Why it's called TV diagram? Because it's a relationship. The y-axis is the temperature, and the x-axis is volume. So these diagrams are named after what is the variable we have on the y-axis, the variable we have on the x-axis. Okay. Let's assume if you need to plot the temperatures here you have. So you have 20 degrees Celsius, right? At state number 1. Then the temperature will increase to 100 degrees Celsius, which is state number 2. Then from state 2 to state 3, do we have any temperature change? 2 to 3. From state number 2 to state number 3, any temperature change? No. So we have horizontal line. From 3 to 4, no temperature change. Once we have state number 4, and we want to go to state number 5, then the temperature will start to increase again. So if you want to plot the TV diagram for this one, will be how it looks like. This is a state number 1 of 20 degrees Celsius. Then the temperature increased to state number 2 at 100 degrees Celsius. State number 3, same temperature. State number 4, same temperature. Then the temperature will increase again to state number 5, which is 300 degrees Celsius. So we have state 2, state 3, state 4. This represents isothermal constant temperature. And this horizontal line is representing the latent heat. Because the amount of heat, you adding heat, just making the phase change. No temperature change. While sensible heat is represented by when you are moving from state 1 to state 2, or from state 4 to state 5. Okay? Clear? Any questions? Okay. So if we have this TV diagram, so again, y-axis is temperature, x-axis is volume or a specific volume, and let's assume we have here 6 cases. We have case A, case B, C, D, E, F. Let's assume we have like any blue color is liquids, the orange color is vapor. So at point number A, at this point, so what will be the phase we have? Liquids or mixture or vapor? Liquid. So this one we will have liquid. So all the system here will be liquid. At case B, what we will have? Still we have liquid. Yes, this liquid is about to vaporize, but we still have liquid. Okay, so this is still liquid. At case number C, we have what? Will be mixture. But do you think the amount of liquid will be more than vapor, or the vapor will be more than liquid? We have more liquid. So this is why we have liquid, and we have very small amount of vapor start to appear. At case number D, we have still mixture, but more vapor. So this is why we have more vapor. Here we have small amount of liquid. Liquid start to vanish. Then at E, we have all of it vapor. And then at F, we have, again, all vapor. Okay, so this one is all vapor. This one is all vapor. Clear? Okay. So, now let's focus on these two things. These two cases and this case. Here in case A we have liquid, right? Also in case B we still have liquid. But do you think these are, well, you can describe these two liquids as the same? So case number A we have liquid, but this liquid you can add sensible heat to it. But at case number B, this liquid, if any heat you add to this one, will it cause increase in the temperature or phase change? Phase change. So you have here one phase, like liquid phase, similar by the way for the vapor phase. So sometimes you have liquid, you can add heat to this liquid, and this heat will cause change in the temperature, like increasing the temperature for this liquid without phase change. But at some position, if you have liquid, if you add heat to this liquid, just phase change will occur. So here we have case number B. We have liquid about to vaporize. So any small amount of heat added to this liquid will cause phase change. But in case A we have liquid. This liquid still away or far away from vaporization. Similar to what we have between case E and case F. So at case E, we have vapor, but this vapor, if we remove any small amount of energy from it, it will condense, right? So this one is about to change its phase. While case F, this one is vapor, and away from phase change. Make sense? Make sense? Okay. So we need to differentiate between them. This is why A, we call this one or this liquid compressed liquid. Or we can call it subcooled liquid. So this name, compressed liquid or subcooled liquid, describe the liquid phase that is still far away from the phase change process. Case B, the liquid phase exists at case number B. This is called saturated liquid. And similar here we have E. This is called saturated vapor. And the vapor exists at case F. This will be called superheated vapor. So here we have four terms: compressed or subcooled liquid. We have saturated liquid, saturated vapor, superheated vapor. So just we need to differentiate between the case that is away from the phase change or the phase that exactly at the phase change condition. Okay? Okay. In the example we said right now, we said just for water, we said for water, at 1 atmosphere, phase change will happen at 100 degrees Celsius, right? So what if we have water but at 2 atmosphere? Do you think the phase change will occur at 100 degrees Celsius or this temperature will change? This temperature will change. So this is also one of the key concepts here, which is called the saturation temperature and saturation pressure. Saturation temperature, this is the temperature at which phase change will occur if or at known pressure or at a certain pressure. Okay? And saturation pressure, also called vapor pressure, this is the pressure at which phase change will occur at constant temperature, which is the case we have. If I tell you I have water, for example, and this water at 100 degree at 1 atmosphere, so the boiling point is 100 degrees Celsius. So 1 atmosphere, this is the saturation pressure or vapor pressure, 100 degrees Celsius, this is the saturation temperature or vapor pressure. Okay? And if we change any one of them, this is the relation between any of them. If you change the pressure, the saturation pressure, saturation temperature will increase. Okay? Just even if this figure for ice, this one for water, so they always have the same trend. Changing any one of them will change the other one. Okay? So if you increase the pressure from 1 atmosphere to 2 atmosphere, then you are expecting a change or an increase in the saturation pressure. So now you can have 2 atmosphere, 100 degrees Celsius, you will still have liquid. But you need to increase the temperature above 100 degrees Celsius, let's assume 110 for example. So 110, this will be the saturation temperature at 2 atmosphere. So always the relationship between them is proportional. Okay? Clear? And again, the saturation pressure, saturation temperature, again, this one, the temperature and pressure at which phase change occurs. So let's assume I have liquid, and here I have vapor. If I have any molecules of this liquid escape to go to the vapor phase, and at the same time I have some molecules from the vapor are being condensed, so now this condition is the saturation temperature and saturation pressure. Saturation temperature and saturation pressure. Okay, you should have phase change. The two phases like exist at the same time. Okay, so far is clear. Any questions so far? So let's recap what we have so far. So we explained what is made by pure substance, right? We said we have 3 categories. You can have substance with fixed composition. You can have homogeneous mixture. Or you can have different phases while the composition between the phases is uniform. Any substance can exist as solid, liquid, vapor, and we can, like any phase, can change to another one. Then, how can we describe this phase change process? We have phase diagrams. We started with the first one, TV diagram. Y-axis is temperature, X-axis is volume, and these phase diagrams, it looks like this one. It has temperature change, then we have constant temperature, that represent the phase change, then the curve will go up like this one again. So this is the TV diagram, temperature volume diagram for any substance we have. This will be the plot if you have pressure 0.1 megapascal. If you increase the pressure to 0.1 megapascal, almost we will have the same trend, except the length of the horizontal line will become shorter, right? So here we have this phase change, horizontal line becomes like more short by increasing pressure. Increase the pressure to 1 megapascal, we have the same line, but this horizontal part becomes what? Right, short again. 8 megapascal, like becomes short, we still have the horizontal line, until we have this horizontal line is represented by a point. And above this point, we don't have any horizontal line. So here, no horizontal line. And if this horizontal line represents the phase change, because this horizontal line we have separated liquid, separated vapor, right? So we have the phase change occurs on this horizontal line. If we don't have horizontal line, so this means we have no phase change. So there are some conditions. Above these conditions, phase change will not occur. And this condition are called the critical point. So above the critical point, you don't have any liquid will exist anymore. No liquid. Only gas phase will exist. Okay? Only below this condition, you can have liquid and you can have phase change between liquid and vapor. Okay? Is it clear? Okay. So this is the critical point, as we said. Above this critical point, there is no liquid phase is existing. And just if you cannot see this one, so this is the critical point. Below this one, we have the horizontal line, and this horizontal line represents the phase change. But here we have the conditions is more than the critical. The temperature or the volume we have here. So this volume is called critical volume. The temperature corresponding to this point is called critical pressure, and the pressure, critical temperature, and the pressure of this line is called the critical pressure. So just look for this point. This represents the critical conditions for your substance. Okay. So if you need, let's assume, for example, you are using the distillation process. Distillation process, one of the like unit operations you are using to separate mixtures based on the boiling point. So you have mixture as liquid. You put this liquid mixture in a distillation column. You try to heat it. Then you try to convert the liquid to vapor and separate the liquid from vapor. So if you have this mixture and you have no idea what is your critical condition, for example, and you decide to operate this distillation column at condition above the critical condition, so will be there any phase change? No. So this point is very important because it becomes, or it defines your limit, especially for the process that you need phase change to occur. Because if you operate any unit above this condition, phase change will not happen. You will not have any liquid. Clear? Any questions this one? Okay. So again, this is the condition: vapor, critical volume, critical temperature, critical pressure. Then, how we get this like curve at the end? So this is the critical point. Oh, let's get back to this one. This is the critical point we have here. And we said this horizontal line represents phase change. Any point here on this side of the line, will it be saturated liquid or saturated vapor? Saturated liquid. Any point at the end of this line here, at this cross, will represent what? Saturated vapor. So if you connect all saturated liquid points then to the critical point, and then you go back from the critical point to saturated vapor, you will end up with this representation of the TV diagrams. So this TV diagrams, then we have this critical point. Any point lies on this curve representing saturated liquid. This is why even this line is called saturated liquid line. Any point lies on the right side of this curve is saturated vapor. So this line is saturated vapor line. Any point in this region, just below this curve, this one will be mixture, two phase, liquid and vapor exist together. Any point in this region is compressed liquid. Any point in this region is superheated vapor. Okay? So again, this one is the same as the previous one, just each color represents different phase. So we have compressed liquid, here we have saturated mixture, here we have superheated vapor. Above the critical point, we can have low density gas-like, we can have high density gas-like, but we will have gases just above the critical point. So each color here represents like different like name of the substances you have. Any questions so far? Is it clear? Okay. So now let's assume if I give you this example and I tell you what will be the saturation pressure at 120 degrees Celsius. Okay. Temperature 120 degrees Celsius. So what is the saturation pressure for this one? Do you think the pressure value will get it from the y-axis? Y-axis is for what? Temperature. X-axis is for what? Volume. So each curve you have represents the pressure. So this curve for certain pressure, let's call it P1. This for different pressure. This for different pressure. This for P3. This for P4, and so on. So now I'm telling you I have temperature 120 degrees Celsius. So almost this is 120 degrees Celsius. This is the figure or the line that represents this temperature. So what is the saturation pressure at this one? What is the pressure at which phase change will occur at this one? So we have this line. So look for the pressure value of this line. So this line is connected to this one, right? And the pressure here is what? 200. So 200 kilopascal, this is the saturation pressure of 120 degrees Celsius. Clear? So what is this critical temperature? Anyone? 350? This is the critical point, okay? So the critical point, this is the critical temperature. Okay, so not this one. And what is the critical pressure? This point. This is the critical pressure. Clear? What is the volume of vapor at 200 kilopascal and 350 Celsius? 200 kilopascal, 350 Celsius. What is the volume? 1.443. So this is 200 kilopascal. This is 350 Celsius. They intersect here. So here you go down, and this is the specific volume you have. Clear? Any questions? Okay. The second type of diagrams we have is the PV diagrams. So PV diagrams, this is what we described. So it said it's relationship between temperature and volume. So when I tell you we have a diagram called the PV diagram, so what will be the y-axis? Pressure. And the x-axis? Volume. And this will be how it looks like. Okay. Here we have liquid. Here we still have liquid. Here we have superheated vapor. Here we have superheated vapor. Here we have mixture region. Still we have mixture region. Saturated liquid line. Saturated liquid line. Critical point. Saturated vapor line. Saturated vapor line. Almost they have everything, right? Except one thing. There is only one difference between them. So how the dotted lines here is moving. So here we start from here, temperature increase, then we have the phase change, then the temperature increase again. But when you flip it to express it as pressure, so what is happening? It goes from up, then down, then go phase change, and then go down. So this is the only thing, only the orientation of the line that represent the phase change of your process. Okay, but except this one, everything is almost the same. Same regions, same lines, same critical point. Everything is exactly the same. And again, for any points above the critical point, so here we have no phase change. So this one, or this region is mixture. This region represents the liquid phase. This one represents the vapor phase. Here we have above the critical point, no phase change. And again, above the critical, here we can see the horizontal lines. And again, above the critical point, when T is more than critical temperature, then we have no horizontal lines will appear. So we have no phase change. Then we have one diagram called the PT diagram. So this one relationship between pressure and temperature, and this one it looks like this one. So here it has the PT diagram. X-axis is pressure, y-axis pressure, x-axis temperature. Here we have 3 points. Again, this is the critical point. This is the, at this region above critical pressure, above critical temperature, we have supercritical fluid. And in PT diagram, we have another point, it's called the triple point. So this point represents the condition at which the 3 phases will exist. At this point, we have solid, liquid, vapor, all of them at the same time. So this appears at the PT diagram. So PT diagram shows to you this one. If you just need to compare the all the diagrams we have explained so far, so let's assume if I have subcooled liquid, saturated liquid, mixture, then saturated vapor, superheated vapor. If I have TV or PV diagram, this will be the points we have. So point number 1, this represents subcooled liquid. Point number 2, this represents saturated liquid. 3, mixture of liquid and vapor. 4, represent saturated vapor. And this one represents superheated. But if we have the PT diagram, so you will see all the points lies on this one. Point number 1, this is the subcooled liquid. Point number 5, superheated vapor. 2, 3, 4, all of them lies on this line. So this is why TP diagram or TV or PV diagram can give you more or better visual way that you can visualize the phase change. Because in PT diagram, all the points or phase change is just represented by a single point. Okay. The last one we have is 3D diagrams. It's PVT diagram. So here we can have pressure, volume, temperature. All of them plotted in the same diagram. Okay. And this is how it looks like. We have a region represent solid, another region represents solid and liquid. Region for the solid, and then we have region for liquid and vapor. Region for vapor, and then we have region for solid and vapor. So everything also is represented with this one. Okay. Okay. Most of the figures we will use will be the first 2 diagrams, which is the TV or PV diagrams. PT diagrams we will not use a lot. These 3D diagrams also will not use a lot in the course. Okay. Any questions? Anyone have any idea or concern? Nothing not clear? Okay, cool. So this is everything.